Hey there, it's Max again. This is the Unlink module first set of slides. Now the Unlink technique is a write, what, where primitive. And it was the first heap exploitation technique that was really well documented in a FRAC article from years ago. So it's done by using the unlink macro when removing a chunk from the middle of a doubly linked list. It's an extremely powerful primitive, but it does have some limitations in which you can actually write to, which we'll talk about later. Now, before you shut this off, you've probably seen this before if you've looked at heap exploitation at all, and this is because this is an older technique, and I know that. However, when I was first creating this course, I thought this technique is actually fairly difficult, and it's one of the more difficult things to grasp. There's a lot of indirection, but I still think it's worth learning. It allows you to understand the malloc source code more. It allows you to travel back in time, and linked lists are actually really common data structures when exploiting C-based programs anyway, so you may be able to use this with something that doesn't actually have protections like modern malloc does. So with that, we're going to go into how to exploit the unlink. So before we do that, we need to talk about consolidation. Consolidation is the process of combining adjacent free chunks. This is done in order to prevent fragmentation. If I had 100 chunks of size hex 20 next to each other, and I wanted to allocate something of hex 100, I have the room for it, I just have these chunks divided. So with the unsorted large and small bin, it will combine chunks together if they're next to each other. Practically what this looks like is we have a chunk that's allocated and a chunk that's free. We then have once we free one of the chunks, they're both sitting there free, and this happens on an individual call to malloc. At this point, we need to combine these together. So it frees it and it creates a mega chunk. That's not a technical term. That's just a max term. Now, this sounds really simple in practice, but you have to remove linked lists, and there's actually some complications to this. So, this happens both when going above and below for chunks. The top chunk is a special case, and if the chunk being freed is next to the top chunk, then that just gets combined with the top chunk. But it should be noted this does not apply to the Tcache and fastbin. For how this actually works, the actual process is that it will remove the chunk from the other bin via the unlinking process. Then it combines the chunks, and then it will add the new combined chunk into the new bin that it belongs to. Practically, how does this actually work? It determines how you can free it using the preven use bit from the chunk above it. So if the chunk above you or the chunk below you, depending on which direction you're trying to free it on, isn't set, then it actually will try to do this consolidation process for you. So we have another code review question, and I need to remove my camera for a second. Cool. So this code is within free, which is noted as _int_free in the malloc source code. Here we have p, which is the current chunk being freed. We have the size of p, which is just size. And then we have chunk at offset, which gets the chunk at a requested offset, which is going to be the size in that case. So my question here is, what is the function call checking here? What is it actually doing? And then 2, how does it find the previous chunk? All right, give you a second, take a second to pause. I think these comprehension questions are really helpful, so think about it. All right, hope you paused and figured this out. If not, that's okay, we're gonna go through it now. So the answers to this is that the first thing is that I need to turn this off again. is the previous chunk free is what this one icon is checking here. It's checking to see if the previous use bit of the chunk we're looking at is set. If it's not set, which is what the exclamation point is doing there, then it means that the chunk is free, which means the chunk below us is free. And now we need to find the chunk below us. So it is doing prev size, is taking the pointer and subtracting it by the previous size. And that then sends us back to the previous chunk. So current chunk minus prev size gives us to the chunk below us. And now we know the chunk that needs to be removed from the linked list. This chunk is already in the linked list, and the chunk that we currently have is the one that we're freeing. So with that context, this is where the actual unlink happens. We need to consolidate the chunks together, and in order to do that, we need to remove the chunk from the linked list, and the unlink macro is now what we're going to talk about. So visually speaking, we have various chunks in a list, and we need to remove it from the list. So we're just going to remove the FD and the BK pointers from the various locations. That's effectively all we have to do. Boom, boom. We have, if we're going to remove the chunk at the bottom of the list, because we need to combine the chunk directly ahead of it, or below it, below it, then we need to remove all those pointers. So we need to remove the bins pointer to it, and then we remove the free chunks pointer to it as well. But we need to swap them in effect. We need to make sure that the linked list is complete. So visually, I think that's how it works. It's nice to see it that way, but actually visually is how this works. You can see here that we just are going to swap pointers. Again, I'm going to have to remove my camera. Boom, boom. So I'm going to pull out my pen, just make this a little bit easier to see. In practicality, what we're doing is we're removing cur. We want to remove cur from the list. So once we're at cur, we want to specify prev's FD to go all the way to next. And now we need to specify next's BK, or back pointer, go all the way to prev. In effect, there's no pointers here anymore. This, as far as we're concerned, cur is no longer in this linked list. This is how it looks cleaned up. So we've shown a lot of visuals, and I think showing code is helpful for how this macro actually works. And this is what the macro looks like, and I've just renamed it because it is such a pain in the butt to actually denote. Because talking about FD's BK and BK's FD, it just makes no sense. So instead of using the actual macros notation, we're going to use something a little bit nicer. Instead, I'm going to use next and prev for this. And I think this makes it a lot easier to read. Again, I'm going to turn off my camera. So we're not going to walk through code-wise step by step what I just showed you visually for this technique. So the first two lines of code are literally just finding the pointers that we need. So we're doing cur of FD is equal to next. And then we are doing cur's BK equals prev. This first part of the macro is literally just getting pointers to the locations. They're effectively temporary variables is all they are. And then after that we start doing the writing. The first part is we're going to set next's BK equal to prev. This is going to remove the back pointer to cur. And then we're going to do the thing in the opposite direction. We're going to set prev's FD equal to next. By doing this, we have now completely removed cur from the linked list as far as the entire linked list is concerned. So just to recap, the cur to FD is literally, sorry, cur of FD and cur to BK is just getting temporary variables. Next of BK equals prev, and FD of prev of FD equals next is where the actual writing happens. And we do this in order to remove the cur element from the linked list entirely. So now, I want you to think about this from an exploitation perspective. And I turn on my camera for this because I think this is cool. What if we controlled the values of next and prev? Well, this is just elements in a linked list, or this is just a chunk. We're just getting next and prev from cur of FD and B of BK. So, if we control FD on this chunk here, well, that means that we control next, and next of BK is being set to prev. That's really crazy, because if we control next, we control where it's being written to, and if we control prev, we control what we're writing, the value of it, which means that we have now constructed a primitive where we can write to any location with any value. And that's enough to pop a shell fairly quickly on anything. So this is where the write what where primitive comes from. Because if we control the value of next and prev, then we control the what and the where. So before, when we had these values that were being written, they were controlled and nice, but now we're doing something evil. So say we're going to do next of BK. Well, in reality, we're doing BK, which is the value, or the location we're going to write to. And then the value is going to be the one that we're actually specifying. So we control the address of both things, which means we get an arbitrary write what where primitive. Again, you can write to almost anywhere in memory. When I say almost, I mean that has to be writable memory. So, and back in the day when there wasn't NX, this is actually a much better exploit. And that's okay. We can still use write what where primitives to do cool things, but we can't just write the address of shellcode like we used to. But we can still do something really cool. So this time I've rewritten the macro one last time to really drive home this write where point home. And I'm going to clean up the diagram just to make it easier to understand as well. And these code comments also have the next and prev, just so you can back reference it. So like before, we're just going to get the FD and BKs. So you could do this in any order, but I'm going to say that cur's FD is going to be the where that we want to write to. And then the cur BK is going to be the what. So once again, the first two steps are just getting temporary pointers to them. And then is where the magic happens. We're going to write where of BK with the value of what. And this is the magic. This is where the actual write happens. And where of BK is just an offset. When you access a structure in C, it's not anything special. It just has some offset to that field in memory. So this offset we'll talk about in a minute. But we're writing where to the address of what, and that's the important thing. And think about this more abstractly. We can write if the where is a function pointer and the what is the shellcode, we can write the address of shellcode to a function pointer and then execute that, which is really awesome. Directly after that, we're writing the value of what plus some offset equal to where. And we don't like that because we can actually corrupt our shellcode with that. So we have to be clever with how we write our shellcode. But this is how the Unlink macro works when we do this. So for some context, you can write to this in either direction. I just chose this arbitrarily because I needed to choose something and go with it. Now, the thing that really trips people up here is this whole structure an offset thing. So when we're writing to P of BK, like we are on this write what where step right here, the P of BK is actually equal to P of hex 18. This P of BK is the same as P of plus hex 18. That's a really difficult thing to grasp. This is because when we do P of BK, we're saying, hey, we're writing this pointer, but we need to find the BK field. When the compiler actually does this, it's just adding hex 18, but humans like reading fields instead of numerical offsets. So, practically speaking, what this means is that we need to subtract hex 18 from the pointer we want to write to. This is because when we do chunk of BK, we're doing chunk plus hex 18 in the first place. So we need to subtract hex 18 in order to counteract this. So when we do the plus hex 18 with this BK, if we subtracted hex 18 in the first place, then they cancel each other out. It's kind of like doing algebra in a way. Now, if we didn't do this, I don't have that. That's okay. If we didn't do this, then what would happen instead is, instead of writing to hex 18 like we want to, if we specified the address we wanted to write to, then we would do the plus hex 18 and go too far and write to the wrong location. So by subtracting hex 18 in the first place, like we see here, then it works out a little bit better. It writes to the proper location. So in order to use this technique, you need to control the FD and BK pointers in a free bin linked list. This can be, there are different ways you can go about doing this, but you need to control the FD and the BK pointers. The different exercises there are two exercises for this, and the different exercises use different ways to do this. You need a known location to write to, which may require a memory leak of some sort, or an information leak, I mean. And then you need a call to free on the chunk next to it. And that's a little bit different. Before, with previous techniques, we've had different requirements, but we need a call to free on the chunk next to it, because it's the actual combining or consolidation process we're exploiting of this. So at this point, this is how the technique works, and we just have exercises to go through. Hope you had a good time. This makes sense. If not, ask questions or read through this or look through this one more time. Thanks.